Okay. Vectors. Yeah. Victor's lesson on vectors. Oh. All right, guys.
And for the people that are watching the recording, my name is Victor. That's the joke. Yeah.
Oh, back there. Oh, I just realized it too.
All right, guys. A vector is different than the numbers that we usually talk about, okay? Units of measure, once we've agreed on the units, you can represent them with a single unit. Things like area, length, time, and temperature, okay? You can give a single unit, and then you add a label, but it doesn't include direction. Things that need to have direction need a magnitude and direction, or a length, or so you could say I'm going to drive 50 miles east, okay? Or I am going to, the ship is traveling at 12 knots, 30 degrees off of north, or whatever. It's something that has both a direction and a magnitude, and magnitude doesn't just mean distance, okay? We're going to talk about it today as the length of the vector, but a magnitude can be in miles per hour. A lot of our questions are going to be in some kind of miles per hour or kilometers per hour or something like that. All right, a vector is drawn as an arrow, but it is not a ray from geometry that goes on forever. A vector has a starting and ending point. The arrow is just there to indicate direction. So this particular vector, if I were to have you measure this in centimeters or something, you would measure from point P to the end of the arrow here at point Q. Okay? So a vector, even though it has an arrow, does not go on forever. When a vector goes from point P to point Q, P is called the initial point, and it is written like this. All right? This is a different vector. Those have the same length, but they're going opposite directions. Does that make sense? If we go from P to Q or Q to P, you're not going in the same direction. But they would have the same length or distance apart. Whichever one is listed first here is called the initial point, and this guy at the back is called the terminal point. Another way of naming vectors is they will use these bold letters here to name vectors as well. This notation that looks like this little double absolute value thing means magnitude. So this is the magnitude of vector PQ, and magnitude means length. For our purposes, magnitude is going to be the length or the distance between the points that are at the ends of the vector. All right, when they use this funny notation, they'll still use these, okay? Everybody good on the vocabulary so far? These are vectors, not on your paper, but these two vectors have exactly the same length, and they're going in the same direction, so they're called equivalent vectors. They'd be parallel in geometry, right? Parallel segments. These are also parallel, but they're not exactly equivalent vectors because the arrow's on the opposite end, so they have opposite directions. Same magnitude or length, opposite directions. These two are going in the same direction, but have different lengths or magnitudes, and these two are not equivalent at all. All right, according to the definition of equivalence, if two vectors are equivalent, then one of them may be moved from one equation to another provided that its magnitude and direction are not changed. That means we can slide things to the origin. Let's talk about this. If I have a vector that starts here at 5, 3 and ends up over here at 12, 7. Okay, I can find an equivalent form of that vector. Whoops, that's not what I meant to do. I can find an equivalent form of that vector by taking that vector right there and sliding it to the origin, okay? What I'm gonna do is say it went over how many and up how many. If this is P and this is Q, and it's going in this direction, from 5 to 12 would be over 7, and from 3 to 4 would be up 4. Is everybody okay with that? So if I slid it to the origin as P, this point Q would be at 7, 4. And we're going to talk about those funny parentheses in just a second. But we're going to do a lot of what's called component forms, and component forms mean we're going to slide it to the origin. Every vector can be written in a form of vector where the origin as its initial point, okay? The magnitude and direction with the origin as its initial point are completely determined by the coordinates of its terminal point. So we're going to take and write that in these funny parentheses, and it's going to be called the components. On your worksheet, I made every effort to use the math equation editor, and so they look like they're supposed to. I will tell you on the homework check, I just used less than, so they just kind of look like that, okay? They don't really look like they're supposed to here, but they're called components when they're written in those. And it just means, like I showed you, let me go back. Here, how I slid it back and it was going over 7 and up 4, these are the components of vector PQ. Even though it originally was going from a 0.53 to 12.7, its x coordinate across was positive 7 and its y coordinate up and down was positive 4. All right. This notation, again, magnitude is the length of the vector. So once we have it in component form, I forgot the numbers, guys. Was it 7, 4 for that one I made up? Okay, if we want to find the length of that, we just do what? Pythagorean theorem, and that's where this comes from, okay? The magnitude is just Pythagorean theorem. Once we've written it in component form, it's a squared plus b squared. If the components are negative, you still will need parentheses to make them positive, okay? Because the length, this should be a positive number. The component form you subtract in a particular order, and I'm going to just show you an example, and that will make more sense. And here are some examples, but we're going to go to ours on our notes. Everybody got this? Okay. This question says we're going to go from A to B. It doesn't have an arrow above it, but it says A to B's components. So I don't like fancy formulas. I like to just think about what we're doing. If we go from A to B for the x's from 2 to -1, what did we do?
Go back 3.
Okay, so we went -3. If we went from A to B with the y's, from 6 to 10 was
4.
+4. If you want to write down what we did, okay, we took the x from B and we subtracted the x from A. And then we did the y from B minus the y from A. And that's how we got the components from A to B. It's like y2 minus y1, okay? I don't like to even think about that. It just hurts my head. I just think about what we're doing. All right, before we go any further, can we jump over here and then talk about what's going to happen when you do B to A? If we're doing the components of B to A, you're looking at these same numbers, but you're going from -1 to 2, so it's going to be, yes, 3. And from 10 down to 6 is going to be -4. All right, so that case, it would be x of A minus x of B and y of A minus y of B. But I'm not going to memorize that. I'm just going to think about the numbers. Okay? The magnitude, what are we going to write in our little box to remind us what to do for magnitude here?
Length.
It is length, so we're going to use what?
Pythagorean theorem.
Yes, we're going to do square root of whatever the components are. So we're going to do -3 squared plus 4 squared, which is
5.
5. If we switch it to BA, does the length change?
No.
The length does not change whether we go from A to B or B to A. All right. Something does change that's going to have to do with the angle, though. This vector, if I had drawn it from 2, 6 to negative 1, 10 over here, would have looked like this. When I slid it to the origin, we said it's really going 3 to the left and up 4. We are going to have to find the angle it makes with the x-axis.
Tan, negative 1.
Yes, we're going to do the inverse tangent. And we're going to basically do y over x. Isn't that the definition of tangent?
Yeah, it is.
Okay. So I'm going to write that on here somewhere for myself so I remember that when I'm doing the angle, I'm always doing inverse tangent of the y. I don't know what I've done. I slid my screencast-o-matic business out of the way here. Can I move you? There we go. Sorry. Okay, and that's going to be the same for here. It's going to be the inverse tangent of y over x. Now, think about this for a minute, please. Is the inverse tangent of negative 4 over 3 going to be different than the inverse tangent of negative 4 over positive 3?
Yeah.
Does it matter when we divide 4 over negative 3 or negative 4 over positive 3? Are those two different numbers?
Nope.
No. So the inverse tangent is going to be the same.
What does it matter, like, that it's going that way or that way?
It does matter. We're going to have to deal with that, yes. Scott?
Okay, two things. For magnitude, you just write 5, you don't write the lines around it.
Right. If you were writing you don't write the lines. The length is just 5. If you were writing the notation, it would say this, but it is just the 5. Yep.
Okay.
What's your other question?
If you can recognize that the
Yes.
components are just parts of a
Uh,
triple, then
Yes. You can also, we're going to do a bunch where there's parts of a special right triangle. And so then you could get to the angle without doing any inverse tangent stuff too. So if we end up with 3 and 3, it's going to be a 45, 45. So you could just say 45 degrees without doing inverse tangent. So yes, there's going to be some where you can skip steps, definitely. All right, guys. The problem is, when we found this angle, did anybody type it in? We want to do this in degrees, by the way. Sorry, I got sidetracked. Inverse tangent of negative 4/3 in degrees gave me negative 53.1. Is everybody okay?
Uh-huh.
Okay. What quadrant is negative 53.1 in?
Fourth one.
Okay, it thinks we're down here. That's because, remember, the calculator has inverse tangent defined in only 2 quadrants, 1 and 4. How do we move it around to quadrant 2?
Add 180.
Yep. Think about your geometry. This is a vertical angle with this, right? So we need to move a straight line across around here, 180. So if we add 180 to this, we now have an angle that's in the correct quadrant, which is 126.9. And that's the angle that we want to say it's making with the x-axis. The angle here, this 53.1, was the angle with the nearest x-axis, but we want to make it clear what quadrant we're in. So we're going to go, it's 126.9 degrees off the positive x-axis. Things change a little bit, though, when we move to B to A, because now you're talking about what quadrant?
Fourth.
BA is actually in this quadrant.
Does it have to be a positive angle?
That's a good question, and my answer for my purposes is no. I will take either one. When you do this, the calculator gives you negative 53.1 degrees. Is that in the correct quadrant? Yes, I'm fine with that. If you wanted a positive answer, what would you do to make that a positive angle?
360.
Add 360. Okay, so I'm going to say or you give me negative 53.1, I will accept that, it's fine. Or negative 53.1 plus 360, which is, anybody have that down? Thank you. Go ahead.
Could you give a negative answer for that one too then?
Yes, you could have subtracted an additional 180.
Or you could subtract it first, like at the beginning, because if you were gonna add 180 and then subtract 360, then you just subtract.
Can you subtract by 40?
Yeah, you could just subtract 180, yeah. All right, anyway, stop, we're hurting my head. All right, you want to try this one on your own? A to B. It's a nice one.
Noise.
Did you get 4, 4? Okay, if we do Pythagorean theorem, some of you will recognize that right away, but it's the square root of 32, which is 4 square roots of 2. It's a special right triangle. If you have two legs that are both 4, it is a 45, 45, 90. You can do inverse tangent, though. Okay, we'll talk about the ACT when we're done taping here, but I do want to get your opinions on some stuff. All right, B to A, what changes?
It goes to -4 to -4.
Does the magnitude or length change?
No. I said no and then you said but. Who doesn't have a but?
All right. When you do inverse tangent of -4 over -4, what happens? Gives you positive 45, is that right?
No, it's supposed to be negative though.
Yes.
Or can you
Why
do-
is there a -4 on the x-axis if it's
Should be positive 3.
Thank you. Totally wrong.
Wait, Miss, how come
I'm awake. Thank you, Victor.
Yeah, no problem. This is all about me.
Yes, it is. So it gives you 45 degrees because it thinks you're in quadrant 1. So what do we need to do?
Yeah, let's
Yeah,
do either
would we
one.
add it?
You could do either one.
You could do either one. Come on, Elizabeth.
I would prefer it was going in the positive direction, but it's not wrong.
Fine. We could go with Pop
Okay? I'm thinking most of you could have done that one without a calculator, if you remember your special right triangles, okay? You absolutely can use your calculator.
Don't skip
Okay,
while you skip. That means-
I'm sorry.
Give me like 2 seconds.
You bet.
All right, thank you.
All right. We are going to spend a lot of time dealing with adding vectors in the next couple days. But today in component form, this is going to be really easy. We're going to talk about adding and subtracting vectors. And they can be multiplied in many ways, but we're going to only do today scalar multiplication. Okay? Scalar multiplication means basically you're taking a vector and making it, if the scalar is 3, you're making exactly 3 times as long. Okay? So if the vector is going through 4, 4, and you do scalar multiplication of 3, it's going to go over 12 and up 12. Okay? If its length was 4 square roots of 2, its length will become 12 square roots of 2. It's just going to be multiplied by that scalar. Here's a quick example of that, okay? If they had a scalar of 3 here, it took the components of 3, 1, and they became 9, 3. If you had a scalar of -2, you would take these and multiply by -2, and it became -6, -2. This shows you what happens if you take v and you multiply it by 3, it becomes 3 times as long. If you take v right here and you multiply it by -2, it becomes twice as long but goes in the opposite direction. All right, when you add, you just add the coordinates. It's that easy. So if you have this vector plus this vector, you add the x's, you add the y's. When you actually add them, we're going to talk about this tomorrow, what happens in terms of when you add a vector v and a vector u that are going in opposite directions, it becomes like the diagonal of a parallelogram. Has anybody had physics? Did you do parallelogram method with law of sines and cosines to add these?
Wait, is it the one where like, I don't know.
Yeah, which is basically a parallelogram. It's just, he might not have called it that. Okay, we're gonna do that tomorrow, but we're also I'm gonna talk about just doing it in component form, which I think is easier, so. And vector subtraction is just adding the opposite of the second one. All right, so let's do these real fast. If you have to add vector u and v, you would do 2 plus 3 for the x, and -1 plus 5 for the y. So what's the components gonna look, what are the answer components gonna look like? Okay, that's it. U minus v.
So -1, -6.
Good job.
Yeah, it is.
All right, and this is the one that's called a scalar, so we're gonna multiply both of the components of u by 3. So it's gonna be 3 times 2, comma 3 times -1. So it'll just be 6, -3. Yes.
If it was 3 UV.
Where there's multiplication going on, that's a whole another ball of wax, and we're gonna do that tomorrow.
Ball away.
Okay, well, actually, we're gonna do adding them in a different form. I'm not sure I know the answer to that question. I'll have to think about that, okay? We're gonna do 2u minus 3v here. We're gonna take vector u and double it. And then vector v and triple it. I always write them down and then I subtract, because otherwise I tend to make arithmetic mistake. Did I do something wrong? Yes, this should be a -2. Thank you, thank you. Doubled that, 4 -2, tripled that, 9, 15. Did that part right. Okay, now I have to subtract them. 4 minus 9 is -5. -2 minus 15 is -17. Okay. E, what does E want for a final answer?
The length.
Yes, the length or magnitude after we have added 2u plus v. So 2u is 4 -2. To that, we're supposed to add a v, which is 3, 5. So we get what? 7, 3. Does that seem okay? But then we need to find the component, or the magnitude of that.
49 plus 9.
58.
Yeah, plus 3 squared. Anybody know what that's close to?
The almost 8, between 7 and 8.
Between 7 and 8, yep. Is it 7.6? Did anybody type it in?
7. No, 7.54. Let me see what this.
I only know because I remember from last period. It's not like I have some extra radical power.
Wait, can you leave it squared? Either.
Yes, absolutely. Either one of these is fine. Yep, I am great. There are going to be some that I ask you to leave in exact form.
That doesn't simplify it, does it?
No, it would be 2 times 29, so there's nothing. Okay. All right. You need to pay attention to this little 2-minute section here, or you're going to be confused in a minute, because I'm not going to do a lot with this. But vector can be written in what are called unit vector form, where I is by definition any one unit in the positive x direction. J is any one unit in the positive y direction. Why they would choose to use I and j when we already know that I is earlier been defined as the square root of -1? But they use I and j, and this time they're called unit vectors. So if you look at this example, 5, -7 can be written as 5i vectors minus 7j vectors, or plus a -7j vectors. That's all they're doing, is writing in the same vector in a different form. I can't tell you when this is used. I should figure that out by tomorrow and try to answer that question for you, when they use which form, but, okay. Given in 10.5, anyway, I don't know. So, we're gonna write this vector how? Anybody know how we're gonna change 3, -4 to ij form?
Yes. 3i minus 4j.
That's it.
So cool.
Oh, you just go.
Make that question 50 points on the next quiz, right?
Yeah.
So what will this one say?
Negative 3i minus 2j.
Is there anything, are they ever going to throw in like a -3 times the square root of I? Or -1?
They could, I suppose, yes, absolutely.
What was the square root of I?
Oh, it would be like 3 square roots of 2 times I or something. There's not gonna be a square root of I in here. All right.
Plug it in.
And that same form, you can add, subtract, multiply, and divide in the i's and j's. It's not anything complicated, okay? This section is given a magnitude and direction meaning angle with the x-axis. Change it to components, okay? So when we're done, we want something that looks like this. All right, let's talk about this. I would like you to be able to do these in exact form when possible. So we're gonna start out, this first one says we are making a 45-degree angle with the x-axis, and we are going out to the tip of our vector exactly 6 units. How are we gonna find the x and y components of that vector? We're gonna make a right triangle, which means we can use what?
45, 45, 90.
It is a 45, 45, 90, so you could just use your knowledge of special right triangles. If it was, say, a 37-degree angle, how would you find this length and this length, given the hypotenuse and an angle?
Sine of 45
Yes.
equals y over 6.
Okay? So to find the x component, that would be adjacent over hypotenuse, okay? So we would use the cosine of 45 is adjacent over hypotenuse, and the sine of 45 is opposite over hypotenuse.
Are we awesome with what?
You are awesome. So to find x, you're gonna do 6 times the cosine of 45. And to find y, you're gonna do 6 times the sine of 45.
Wait, every single 6 divided by square root.
Yes. Can we substitute a value in from our unit circle? If we're gonna do these exactly, we need nice
Power of 4.
exact values. This is 6 times the square root of 2 over 2, which is 3 square roots of 2.
Beautiful.
This is also 6 times the square root of 2 over 2, which is 3 square roots of 2. If you don't have your unit circle out, you might want to grab it.
What's a unit circle?
5 times the square root of 3, comma, 5 greater than.
Okay, this is a vector that's 10 units long, making a 30-degree angle. It is a 30, 60, 90 if you know that. Shh. I'm trying to get you to see the generalization though that has to do with sine and cosine.
Well, we see that, but why
Okay.
do all that work if we
You're absolutely right, Victor. If you know your 30, 60, 90s and 45, 45, 90s, I wouldn't bother to do this.
Which I mean, I don't.
But when it's gonna be, in a minute, when I ask you one with a 22-degree angle, you're gonna need to know that it comes from, okay, the length of this, which I'm gonna call R. Remember when we talked about this point as like x squared plus y squared equals r squared? If we had a circle that went through there, it would be the radius. I'm still just gonna call it R. If you do r times the cosine of theta, you will always get the x coordinate. And if you do r times the sine of theta, you will always get the y coordinate.
R is the hypotenuse?
Yes,
Okay.
this is the length of the vector, basically, okay? If we had a circle that went through this point, it would be the radius. That's why I'm gonna use r. When we do polar stuff, it's called r. So I'm just going with that same format, so we don't have to write it 10 different ways. All right, so the cosine of 30 degrees and the sine of 30 degrees, anybody?
What? Oh.
What were we doing? X equals, wait, no.
Cosine of 30. Anybody have it out? Then get square root of 3 over 2, and the sine is,
Yeah. 1/2.
so 10 times the square root of 3 divided by 2 would be
5 squared is 3.
5 square roots of 3 are our components, and 10 times a half
5.
would be 5. And again, several people have said, this is the hypotenuse, that means the short leg is half that, and the long leg is 5 square roots of 3 if you were using your special right triangle stuff, if you remember that 30, 60, 90 stuff, which I just taught today in geometry. All right, question C. We are in a different quadrant, right? We are down here at 225 degrees. Now, if we use 225 degrees,
It's like a 45 degrees.
it will give us the right signs, okay? It will take care of, now, most of you know what are these two gonna be?
45, 45.
Yes, 45, 45, 90, so both the legs are gonna be
6.
6. So in this quadrant though, the signs would be
-6.
if you just bear with me for 1 second, if you had done 6 square roots of 2 times the cosine of 225, that would have been 6 square roots of 2 times a negative square root of 2 over 2. 2, not 3, there we go. So you would have gotten 6, negative 6, square roots of 4 divided by 2. Square root of 4 is 2. That would divide out, you'd get negative 6. And the same thing would happen for the other one. You could have also typed on your calculator 6 times the square root of 2 times the cosine of 225 or times the sine of 225, and you would have gotten these answers, okay? All right, you guys try this one on your own. 8, 120. Try to give me exact answers, okay?
This would all be in degrees, correct?
Yes, these are degrees. Anybody come up with answers?
Definitely.
What'd you have, Mary?
-4 and 4 squared.
Okay. A lot of you would have recognized again the special right triangle. This is a hypotenuse, so half of that goes here, and the short leg times the square root of 3, and you're going left. Otherwise, if you had pulled it off the unit circle, you would have got -1/2 and positive square root of 3 over 2, which simplifies to this. You don't have this question, okay? You don't have E and F on here. And I'm gonna, oh,
Ugly.
and I want to change this if I can get it to go in there. Could you just do these? You don't even have to write them down, but help me do these two. They're going to be, are they going to be exact values? No. So they're really easier than anything we've done. All you have to do is type what?
12 times the cosine of 22 and 12 times the sine of 22.
Okay, can you give me some decimals?
Where's it at? Can I have it now?
No, you don't. Anybody getting anything? 11.1 and 4.5. Did anybody type that in for me? Get that? Checking my math. Okay. I changed this so it says 156 degrees. Let's see if it gives us the right quadrant. Okay? 10 cosine of 156. Anybody type that in? What'd you get?
Better be
What'd you get?
negative.
And 10 sine of 156?
Yes.
Okay.
Students take calculus.
If we went around 156 degrees and out 10 units, does it make sense that this would be negative 9.1 and up 4.1?
Yeah, do it.
Okay, so the good news is when you use this format, it will give you the right signs on the angles, okay? As long as you're measuring off the positive x-axis, it always gives you the right sign. All right, moving on. These are going the other direction. We've actually already done this once today, but this is just a different way they will ask the same question, so I wanted to show you a couple examples of this real fast. If we know the component form is 4, -4, we need the magnitude, so we need to do what?
Just sine or cosine. Oh, bigger, yeah.
Okay. The magnitude of V is going to be what?
4 square root of 2.
Yep, square root of 32, right? 16 and 16, which is 4 square roots of 2. And how do you find the direction?
I don't know. What is direction?
Direction
Oh,
means
the
angle.
Tan of 1. What is tan of 1? Negative 1.
Inverse tangent of y over x gives us
Yeah,
negative
that's what I
45
got.
degrees. Yes, is that what you got? If you didn't, we need to know. Inverse tangent of -4
Oh,
divided by
inverse. There you
4.
go.
Okay?
So that's 300.
Is that the right answer?
Yeah.
That is a fine answer, because it's in the right quadrant. Or you could add 360 and say 315 degrees.
And it has 2 equal side lengths.
Number, or part B, you need to do less thinking.
Not possible.
If you go from the origin out to -3, 0, what is the angle it makes with the positive x-axis and how long is it?
180.
180.
The magnitude is just 3, and the angle is 180 degrees. By the way, if you did inverse tangent of 0, can you try it? Inverse tangent of 0, it works, but does it give you the right answer?
0. No, you gotta add 180.
Yeah, gotta add 180. But it works, it's not undefined or something, okay. What about this one?
Ugly.
Is it 8?
Yes. 4 and negative 4 square root of 3 is a 30, 60, 90 again.
Oh, I
If you
didn't
did,
realize
it's kind of messy, but it will come out 8 for the
that.
magnitude.
Negative 60.
And if you do inverse tangent of negative 4 square roots of 3 over 4, or just negative square root of 3, you get negative 60 degrees. Is that an okay answer, guys? Is it in the right quadrant?
Yeah.
Or you could say 300. Either one is fine. Is this last one a special triangle?
No.
Yeah? Is it a triple or no?
No.
Is it?
No. Square root of 41 is ugly.
Okay, the magnitude is the square root of 41. And the angle in here,
Uh, 128.659.
okay, when I type this on my calculator, I get negative 51.3.
Add 180. Well, now add 180. That's all I think.
Yes, to get it over to this quadrant, we need to add 180 to that.
Isn't it 129.6?
128.7?
0.7?
Wait, what
Well,
is
it was 0.34, so it's 0.66 or 0.7.
Dang it, I put
What do we have on the, 51.3, okay, cause that.
All right. As of today, you can do all of those problems underlined in red on 10.5 and 10.6. Those are listed on the first sheet. Did I point that out already? They were at the top of the first part of the notes. I don't have a pink assignment sheet for you on this, okay? Sorry. We're finishing chapter 10. These are the 2 sections we're doing. It's written at the top of the notes worksheet today.
That makes you want to take a picture.
You may.